let's try to show the continuity of the function square root of x at x equal to 0. Now, in our calculus topics, we're able to identify that the function f of x, we have here f of x is equal to square root of x is really continuous at a certain interval. You will have that here, 0 to positive infinity, right? Because it will make our function defined if we are not going to use negative values for x's here. Yes, that's true. But this time, we are going to show the proof of this using the definition itself. The definition of a function being continuous at certain c. I'm going to write here just a portion of the proof, I mean the statement of this continuity of a function at a number, because we will have a separate video for that already. So here is its statement. So this is a snippet. If for every epsilon greater than 0, there exists delta greater than 0 such that if x is a point in subset of real numbers, which is a, satisfying this distance of x and c less than delta, then we have here f of x minus f of c must be less than epsilon. This is the portion of the definition. I just removed there that a is a subset of real numbers, and we let function be a mapping from a to our set of real numbers, and the existence of c, element of a. But basically, again, I'm just writing this for the purpose of guidance for our proof. We have a separate video for the definition itself, so you might want to review that. Here, we're going to use this definition in proving this continuity of this given function here. Take note that our f of x is equal to square root of x is already here. Our f of c later on, okay, where our c is equal to 0. This is where we are trying to show continuity. So we'll have here square root of 0 or just equal to 0 itself. So we're going to use the definition here. But of course, since there is a claim that there exists a certain delta, okay, this delta here, so we need to show the value of the delta as well. So similar to what we did in limits, in proving limit theorems, using definitions and such, we can try here coming up with a scratch work. Okay, so let us also have a scratch work here. This is our goal. We would like to reach into that so that we will be guided on what would be the appropriate steps. So if it's f of x, we know that's actually square root of x. And our f of c is square root of 0 or just simply equal to 0. It's still less than epsilon. You would like to come up with an expression similar to this, x minus c, in this form, so that we can actually come up with the correct form of delta we are going to use, because there exists a certain delta. Delta must be introduced here. So simplifying this further, you have square root of x minus 0 less than epsilon. So you have here absolute value of square root of x is less than epsilon. Okay, so since this is just square root of x still, what we need to do here is to come up with x minus c here. So in short, we just need, because if x minus c, if we have x minus c, okay, less than delta, we know that our c is 0, so absolute value of x must be less than delta. We would like to see something like that here, but it's a square root, so we can actually simplify the absolute value. It's just square root of x less than epsilon. Okay, so we'll have here square root of both sides. X is less than epsilon squared. Now take note, the absolute value of this is also x less than delta. Following the relationship, we can now say that we can assume delta is equal to the epsilon squared, so that this will too be matched. Now that we have established existence of delta, we can now proceed with the next steps, because that's the important part of our proof. The existence of delta, in this case, we have introduced epsilon squared. This time we can now start with our proof. Our proof will start with the existence of epsilon greater than 0. So let epsilon be greater than 0. Then the existence of delta. Assume delta is less than epsilon squared as indicated here. Since delta is now existing, then we cannot continue with the statement. If you will have here x minus c is less than delta, or if you would like to, you will have x minus 0 less than epsilon squared. You can have that, or you can even have this x. We have you have here the absolute value of f of x minus f of c. Take note that we would like to reach this one here. So this is equal to the absolute value of square root of x minus square root of 0. And then this is equal, this is also the other purpose of your scratch work. You will be guided. This is just absolute value of the square root of x. And with that now, we know that this could be equal to just a square root of x right now. Now, when do we get square root of x? Take note that we can also write it like this. The square root of, you have here, your x inside. Okay? You have here the value of x inside, which is actually less than epsilon over 2. That would mean this is less than the square root of, you have here, epsilon over 2, which will give us a result of epsilon. The main goal here is to make sure that the end part of this is just epsilon as indicated in our target here. So you just need to look into the appropriate relationships. And take note, this was actually taken from this relationship here as well, because this is x less than epsilon squared, as you declare earlier the delta itself. So we're just trying to, this could be written, if you would like to, x to the power of 1/2, right? Okay, so you could also have here x, since x is, I'm going to write here another process if you are not convinced with that. This is less than, you have your epsilon squared raised to the power of 1/2, which gives us still epsilon. Now, bottom line, we just aim to target this from here to meet the definition of continuity. So hence, we can construct it here. Hence, our absolute value of f of x minus f of c is less than your epsilon, the intended target now of our goal. Now, after this, we can just simply say, since epsilon is greater than 0 is arbitrary, then we conclude that, okay, we have here the, what do you call this one? We conclude that x is continuous, square root, sorry, f of x, which is equal to x, square root of x, is continuous at x equal to 0. This is the proof of this problem. Of course, again, as mentioned, using calculus concepts, we're able to show that it's really continuous at this interval. But this is using the proof of the definition. Thank you very much for watching.